Welcome back, everyone, to today's Explainer. I'm absolutely thrilled to dive into a topic today that is quite literally foundational to our modern world. We're talking about topic 19, caissons and well foundations. It's all about that hidden, colossal engineering that happens deep beneath the surface of the water and way underground. So, I want you to just picture a gigantic bridge spanning across a raging, incredibly deep river. Think about the sheer, mind-boggling physical challenge of supporting thousands of tons of steel, concrete, and moving traffic over deep water or really soft, unstable soil. How on earth do engineers build a stable base in those extreme conditions? Well, today we're going to uncover exactly how they pull that off.
Okay, here is our roadmap for today's Explainer. We'll start with deep foundation basics, then move on to exploring caisson types. After that, we'll look at working under pressure, shift our focus on well foundations, and finally cover their anatomy and construction.
Let's kick things off with Section 1, Deep Foundation Basics.
You might be wondering what exactly separates a standard, everyday shallow foundation from a deep one. The math is actually wonderfully simple. A deep foundation is just defined by its geometry. It's one where the depth of the foundation, marked as df, is strictly greater than its width, which we mark as b. If the depth is less than or equal to the width, you are looking at a shallow foundation.
Now, when we talk about deep foundations, we're generally talking about using piles, piers, caissons, or wells. Obviously, these aren't for your average residential home. They're designed to carry the absolute heaviest of loads, like those enormous bridges we just talked about, or towering multi-story buildings. But here's the really crucial distinction. While piles are relatively long, slender members that are driven into the ground, piers, caissons, and wells are much, much larger. They are immense, bulky structures constructed by heavy excavation and sunk deep into the earth.
Moving right along to Section 2, Exploring Caisson Types.
So the word caisson literally translates to a large, watertight chamber. And what's really interesting about their taxonomy is how clearly it breaks down. Engineers classify them into 3 distinct types based on how they're built and installed. And it literally all comes down to what is open and what is closed during construction. An open caisson is essentially a massive box that's open at both the top and the bottom. A pneumatic caisson is closed at the top but open at the bottom. And a floating or box caisson flips that completely. It's open at the top but permanently closed at the bottom.
Let's look a little closer at the 2 most contrasting types, open versus floating caissons. Open caissons are designed to actively penetrate the soil. As the earth is excavated from the inside, the caisson slowly sinks. Once it reaches its final design depth, engineers place a massive, thick concrete seal right at the bottom, directly in the water. Floating caissons, on the other hand, are totally different. Because they have a closed bottom, they don't penetrate the soil at all. Instead, they just rest flat on a hard, level surface. Because of this, their load-carrying capacity relies 100% on base resistance since there's zero friction along the sides from the soil to help hold them up.
Now, this builds into one of the most fascinating processes in all of civil engineering. Sinking a floating caisson is basically like treating a towering concrete foundation like a ship. First, it's cast completely on land, and if it's going into rough waters, it's even designed with internal strutting, exactly like a ship's hull. Second, it's literally launched and floated out to the exact construction site. Third, it gets sunk into position. But here's a wild fact for you. They almost never use concrete to sink it. Instead, they fill the inside with sand, gravel, or even just water to weigh it down. Finally, they place riprap, which is a thick layer of large rocks, all around the base to prevent scour, which is the destructive washing away of the soil by river currents.
All right, Section 3, Working Under Pressure.
So what happens when the soil is way too soft? The risk of scours is simply too high, and engineers need absolute control at the very bottom of the river. This is where the pneumatic caisson comes in. Remember our table? Closed at the top, open at the bottom. Down at the very bottom of this structure is a working chamber. Engineers pump compressed air into this chamber at intense pressures, up to 350 kilonewtons per square meter. That extreme air pressure physically pushes the water and the mud out, allowing workers to excavate the earth in completely dry conditions, even while they are incredibly deep underwater.
Obviously, while this gives engineers incredible control over the foundation, it introduces some very real human risks. This brings us to caisson disease, which you probably know as decompression sickness, or the bends. Because workers are operating under intense compressed air, coming back to normal surface pressure too quickly can be highly hazardous and sometimes even fatal. Because of this, pneumatic caissons require extreme safety precautions, specialized airlocks,
and heavily restricted work schedules to keep the crews safe.
Next up, Section 4. Focus on well foundations. Moving away from those pressurized depths, let's look at a specific type of deep foundation that is incredibly popular, especially in places like India, for supporting bridge piers and abutments. You might be wondering, why call it a well? Well, it actually derives its name from traditional underground water well construction techniques. But in geotechnical engineering, well foundations are monolithic, immense, and highly rigid structures. Structurally, they behave very much like the open caissons we discussed a minute ago, coming in a variety of fascinating shapes, from simple circles to double D or dumb well shapes to best fit the heavy load sitting above them.
Now, if you are an engineer planning a monumental structure, why would you choose a massive well foundation over simply driving piles into the ground? There are some major advantages here. First, that sheer size and rigidity makes it incredibly effective at withstanding scour. Second, because it is open, engineers can literally inspect the soil as they sink it, ensuring they hit the absolute perfect bearing stratum. Third, it can withstand extreme lateral loads. Think of the powerful, relentless side-to-side forces from rushing river water or intense wind against a bridge pier. And finally, unlike driving piles which physically shake the earth, sinking a well causes zero vibration damage to any adjacent structures.
Finally, let's get into Section 5, Anatomy and Construction.
So how exactly are these underground wells put together? Let's quickly break down the anatomy so you can grasp the specific vocabulary engineers use. The main body or the wall of the well is called the steining. At the very bottom is the cutting edge, which is heavily reinforced to actually slice right into the soil. Just above that cutting edge is the curb. Once the whole structure reaches the final depth, the bottom is plugged with a concrete seal. Finally, sitting on top of the steining, right around the low water level, is the well cap. This cap acts as a thick structural slab that takes all the weight from the bridge above and cleanly distributes it down into the well.
And this brings us to a really vital term for the safety of the entire structure: grip length. This isn't just the total depth of the well. It is specifically the depth of the well foundation below the maximum scour level. Rushing river water is unbelievably powerful, strong enough to wash away the top layers of the riverbed. If the grip length isn't deep enough below that eroded line, the entire bridge could be compromised by lateral forces and tip over.
So how do they actually force this colossal concrete body deep into the earth? The sinking operations are honestly a total feat of mechanical ingenuity. First, they excavate soil from the inside through what are called dredge holes. Often, the well just sinks under its own immense weight, sometimes dropping half a meter just on its own. But when it gets stuck, engineers add kentlage, which is essentially just stacking vast amounts of extra dead weight on top to force it down. And if the soil friction on the outside of the steining is still too strong, they literally pump high-pressure water jets along the exterior surface to lubricate it and reduce that skin friction.
It really is an incredible dance of weight, physics, and deep earth mechanics. Which leaves me with this final thought for you. The next time you're driving over a towering bridge, looking at the water rushing below, will you think about the hidden engineering marvels, the massive caissons and the well foundations buried deep beneath the surface, making your safe passage possible? I know I for sure will. Thank you so much for joining me on this explainer, and keep looking beneath the surface of how our world is built.